All right, how's everyone doing? So the plan today is to just keep on with chapter 25. We were discussing potential energy of charged particles. Today we're going to do a few more problems with potential energies, and then we're going to jump to talking about this concept of electric potential and keep going with problem solving. Okay, so that's the game plan. So let me just get my screen sharing. Okay. And make sure I can see the chat. All right, good. All right. Great. So chapter 25, we were talking about electric potential and we ended up yesterday on this problem. We were talking about a charged particle, right? Two objects with spherically symmetric fields around them that are interacting. And we wrote down a functional form for the potential energy between those two objects. We wrote down this thing that the potential energy looked like K, Q1, Q2, the product of the two charges divided by R. Okay. And for this first problem, we said if it's two positive charges, right, that we could make a graph of that potential energy as a function of the separation between the two particles, and then it falls off with this 1 over R behavior, right? So as the two like charges get closer together, then the potential energy between them is growing, right? Because you're moving them closer and closer against the direction that the force is pushing them away. So you're doing some negative work to them, and that means you're increasing the potential energy. And as they get further away, that right, as R becomes huge, that potential energy goes to zero. So out at infinity, when the particles are very far away, there's essentially no potential energy between them. There's no stored energy. What about this last question? What if the large fixed charge was negative instead of positive? What does that change about the potential energy in this problem? Well, we can think about this. The first thing is, does the particle speed up or slow down? Well, now if that's a negative charge, right, there's an attractive force. So we have this idea that the particle should be accelerated towards that negative charge and it should be speeding up, right? We can explain that with the forces. We can also explain it with the electric field. There's a field that points inwards towards this negative charge. That means that this guy is going to experience a force that's equal to its charge times the electric field. It's going to point towards that negative charge. That's going to establish this force and the acceleration that's going to speed it up. And now we can also talk about the energies, right? We can see that as I move this thing, right, displace it in this direction D, the force and the displacement are aligned. So the work, right, I know that the delta potential energy, the change in the potential energy is minus the work. Because the force and the displacement as I move towards that negative charge are in the same direction, the potential energy has to decrease. Right? The work is positive, the change in the potential energy will be negative. That means my object has to be speeding up. I see the potential energy is dropping, so my kinetic energy has to be increasing. What about a plot, right? This plot of the potential energy as a function of R. How does that change for these when I make the negative object, when I make that larger charged object negative? Well, the only thing that changes is that now this second charge will be negative. I have one positive charge and one negative charge. So that means the potential energy in this equation between the two will be negative. Right? And I could draw what that looks like, right? If I have K, Q1, Q2 over R, one of them's negative, one of them's positive, and I plot that potential energy as a function of R, okay, well, it's going to be negative. Look, when this guy gets really small, right, this is the potential energy. When R gets really small, that means the potential energy gets really negative, right? This has got a negative, right? A negative value times a positive value. The magnitude of that gets really large. I get to really large negative values. As r gets very large, again, I approach 0. And so I have a function that looks just like for the positive version, but flipped over that x-axis. So as I approach, right, as I'm approaching that dissimilar charge, my potential energy is increasing. But again, as I move further and further away, my potential energy is running to 0. Okay. All right. So what about this example here? I have a positive charge and a negative charge, and I hold them initially at rest, and then I release them and I let them start moving towards one another. What happens to their potential energy as they move towards each other? It becomes more positive, less positive, negative potential energy. Oh, sorry, a positive potential energy becomes more positive, positive potential energy becomes less positive. The C and D are the same thing, but with negative potential energies. Let me start the poll and see what you guys think here. There we go. Okay, let's go ahead and end the poll. So most of you selected C, right? So this is just what we were talking about. U is going to equal to minus K, the magnitude of whatever that positive charge is, times the magnitude of whatever the negative charge is, right? The negative sign is popping out in front here because I know I have one positive charge and one negative charge over R. Okay. So that means as they, right? So first of all, I know that it has a negative potential. I see since I have two oppositely charged particles, that leads to a negative potential here. Okay. Negative potential energy. And as R gets small, right, the R, the separation between them is decreasing in this case. As that goes down, the potential energy is going to be going up. So this thing is going to become more negative as we go along. So we have this nice functional form for the potential energy coming from the charged particles. Let me look at the chat real quick, see a couple comments. So Jacob says, I'm a little, okay. Sorry, Jacob. On this previous problem, the positive charge approaching the positive object does not speed up. That's the example we did today. We were doing this lower bit where we flipped that large negative object to a negative charge. Okay, so if you want to see the positive charge interacting with the large positive object, that's what we worked through yesterday. Today we just were quickly going through what happens if that large negative charge is negative. Okay, does that make sense then? Let me know if you still have your question, but otherwise, okay. Yep, no, you're good. Okay, great. Okay, so let's try to do a problem that's a little more quantitative. So let's imagine that we have a bead, some plastic bead, and we charge it up. We put some excess negative charge on it, 1 nanocoulomb, and we know the size of the plastic bead is 2 millimeters. And what we're going to do is we're going to take a proton and we're going to fire it towards that bead, that charged object, from far away with some known initial speed, 1 × 10⁶ meters per second. And it's going to strike that plastic bead. Okay. What we want to do is try to find what is the speed with which it will be traveling when it hits that bead. Okay. So let's work through together how we're going to do problems like this. So when we're looking at problems with energies and also with potentials that we're going to see as we move along here, remember that we're only interested in the initial state and the final state. Okay. The details of what happened in between, shouldn't matter because of right, energy conservation. If I can understand the initial energy I have in my system compared to what the final state of the system looks like, and then I can do some energy conservation to understand that system. So what you should always be thinking about doing is breaking the problem up into states, right? What does the problem look like in some initial state? We'll call I. And what does it look like sometime later when I'm interested in the state, interested in the system? We'll call that F. Okay. And so we have a charged object here, minus 1 nanocoulombs. And we know the size of this thing is 2 millimeters. And that thing's just sitting there at rest. And initially there's a proton over here, right, that has positive fundamental charge sitting on it. And it has an initial velocity in this direction headed towards that guy that we were told is 1 times 10 to the 6th meters per second. And then some time elapses, right? And they tell us that this is very far away to start. That's all they say. So when they say very far away in your book, we're going to just take this to be some huge number. We can just think about that being like some infinite value, some huge number. We're going to see that's important when we talk about the initial potential energy of the system. And then some time goes by, and we relook at our system, and we see that the system is evolved, and now that proton is right at the surface of this charged object, and it has some, what we'll call V final in this direction. Okay. So let's try to solve this problem using energy conservation. Energy conservation tells us if we can calculate the kinetic energy that there was in the system in our initial state and the potential energy that was available in the initial state, then that should be equal to the kinetic energy in the final state plus the potential energy in the final state. Right? That's a statement of energy conservation. So let's see if we can write down each of these terms. Well, in the initial state, we can write down the kinetic energy. I have 2 objects in my system, so I should check to see if either of them or both of them are moving and have some kinetic energy. Well, the large 2 millimeter charge is just stationary in this problem, so there's no kinetic energy associated with this guy. But this guy, the proton, has some initial kinetic energy. What does that kinetic energy look like? It's going to be 1/2 the mass of the proton times that initial velocity, 1 times 10 to the 6th meters per second. Right, squared. 1/2 mv squared. That's our kinetic energy for that proton. What's the initial potential energy for this system? Okay. Well, we can calculate that using the formula that we've been writing down, right? It's K, our physical constants, times Q1, right? That's going to be positive fundamental charge on the proton, times Q2, that's going to be my minus 1 times 10 to the minus 9 nanocoulombs. And all of that over R, which is the separation between them. But now in this initial state, R is just infinite. Okay, some huge value. It says take R to be gigantic. So this guy is just going to go to 0. So in that initial state, because the particles are very far away, they are very weakly interacting with one another, generating some potential, but it's very small. So we basically assign 0 initial potential energy. It's small compared to the other energy quantities in the term. And so all of the initial energy of the system is in that kinetic energy. Okay, great. And now what do we have to do? We have to set that equal to the final kinetic energy. That's going to be 1/2 the mass of the proton times that final velocity squared. And look, this is exactly the bit that we're looking for. What is that impact velocity? Right, that's what the problem asked for. What am I going to write down for the potential energy here? Well, it's going to be K, the fundamental charge of the proton, right, positive, times a negative 1 times 10 to the minus 9 nanocoulombs. all of that over. What am I going to write for the separation distance, right? It's K Q1 times Q2 over R. What's the separation distance that I'm going to use in this expression? What goes in here? Any ideas? If somebody wants to, okay, yeah, radius of the bead time plus the radius of the proton. That's what people are saying, right? The radius of the proton, we're going to ignore the radius of the proton. You could go look up what the average radius of a proton is. It's incredibly small, and it would be out at, right, like it's like femtometers. It's like very, very small. So we're going to neglect the radius of the proton and just use the radius of this object, right? Remember that the electric field outside of a charged sphere looks like the electric field coming from a point charge that's sitting right at the center of that charge. And that R in the potential, right? So that R is the separation between, right, in this U equals K Q1 Q2 over R. This R is distance, right, between, between the centers of the objects, right? The distance between the center points of the objects. So if I have a large extended object, right, I can never get all the way to R equals 0 because I'll physically hit the object. I'll strike the object before I get to the center. So this R has got to be R1 times 10 to the minus 3 meters. Okay. And now we have a nice expression that I can use to solve for V final, right? All I need to do, I'll leave the algebra up to you, right? All I have to do, right, everything here is known. I can look up the fundamental charge. I can look up K. I can calculate this value. Same thing with this bit. I can look up the mass of the proton, and then all I have to do is solve for V final here. Okay. So this is the really nice thing about energy conservation laws, that usually I end up with one line that I can have a single unknown and solve for, right? Solve for some velocity that I'm trying to find like this. Any questions about how we set that up? All right. What's the second part of this example? The second part says an electron is fired at the same bead from far away. And it says it reflects with a turning point 0.1 millimeters from the surface of the bead. Can we determine the initial speed of the electron? Okay. So this is a really similar problem. Let's set up our initial and final states again. Again, now we have an electron over here. So it has minus a fundamental charge sitting on it. And we have our -1 nanocoulomb bead here. And it says this thing is going to move towards here, right? It's going to keep moving until it gets to, right? Sorry, this is our initial state. So there's some initial velocity. And in this example, we don't know what that initial velocity is. But we know that at some later time, we observe this system, and that electron has gotten closer to this charge. And at this point, right, it's, okay, so it says there's a turning point at 0.1 millimeters. What does that mean, that there's a turning point? What does that tell me about the electron in the final state, that there's a turning point at 0.1 millimeters away from the surface? Changes direction. Yeah. What does that tell me about its velocity? Jeremy's saying that the velocity is 0, right? We know that its velocity, the turning point means it switches direction. So that means its velocity goes from pointing towards the -1 nanocoulomb charge to pointing away from it sometime later. So right at that point, right at that turning point, the velocity has to turn from being, positive to negative or negative to positive, and that means it has to go through 0. So we know that the electron has a velocity, a final velocity of 0 right here. And that's happening 0. What is it? 0.1 millimeters away from the surface of this sphere. Okay. And this is still a 2 millimeters across. And again, it says that this starts very far away, so r equals infinity in this initial case. Okay, so now that we have our initial state and final state diagrammed, let's go ahead and do an energy conservation. It's going to, again, just say that the initial potential energy plus the initial kinetic energy has got to be equal to that final potential energy plus the final kinetic energy. Well, what's our initial potential energy? Well, R is infinite, and our functional form still tells us that that has to go to 0. What's our initial kinetic energy? Well, we don't know. We know this is going to be 1/2 the mass of an electron now, because we've switched particles, times that initial velocity squared. And again, this is the variable that we're trying to solve for in this problem. And that has to equal, well, the final kinetic energy is easy. That's just 0 because I see the velocity is equal to 0. What about the final potential energy? Well, I know I can just use my functional form for the potential energy for two objects with spherical symmetry approaching one another. It's like K. Now I have minus a fundamental charge times my negative 1 times 10 to the minus 9 coulombs. All of that over R. What's my separation now? Remember, we're trying to find the separation between the centers of the two objects. Okay, so that's going to be like 1 millimeter, 1 times 10 to the minus 3 meters, plus I got to add this extra distance that I am away from the surface here, plus my 0.1 times 10 to the minus 3 meters. Okay, now I'm done. I have a pretty simple equation this time. I can calculate everything on the right-hand side here, right? There's just a bunch of physical constants that I can go look up and quantities that were given to me in the problem. And then I just have to multiply by 2, divide by the mass of the electron, and take the square root to find that initial velocity. Okay. Make sense? Should look very familiar to what we did with energy conservation problems in Physics 313. It's just now we have a special functional form for this potential energy between the two charged objects. Okay, good. There is a example in your book, if you would like to see this written out in some other detail that's essentially identical to that problem that we just worked through. It's example 25.2. So I'm not going to rework it. It's the same problem. But if you want to review this in your textbook and have sort of another step-by-step version of it, that's an example you could go take a look at as well. Okay, your book does a few other examples that I can point to. One is this escape speed problem. So I'm not going to write out the full problem, but let's just look at the solution, and you can read through this in your textbook. This says I have two elementary particles. An interaction between two elementary particles causes an electron and a positron. A positron, it tells you, is an object that has the same mass as an electron, but with an opposite charge, with a positive charge. And they to be shot out back to back with equal speeds. It says, what is the maximum speed each must have when they are 100 femtometers apart in order to escape each other? Okay. So this is, what does this mean to escape one another? Well, we looked at this when we were discussing gravity, or maybe you did in your 313 class. You can have a massive object that's trying to leave the surface, right, of say the Earth, and it has to have a certain amount of velocity in order for it to, quote unquote, escape the gravitational attraction of that first object. And basically it just means they need to be able to get out to this infinite, right, to this very large separation so that the potential energy essentially turns off between the two objects. Okay. So let's see, how would we set this up? We would do it just the way we did the previous problems. We would draw a before and after picture. So initially we have a positively charged object and a negatively charged object. They give us the separation between those two particles, and we're trying to find, right, it says that they're fired off with the initial speed. We're trying to find this initial velocity. And what we know is that they're supposed to have enough velocity to escape each other. So here's a diagram of what it means to just barely escape from each other. It's that at some later time I look and the particles are off at very far distance away from one another. Okay, so that potential energy has gone to zero. But at that point, they've just exhausted all of their available kinetic energy. So you see that their velocities are turning off. If they had extra velocity, that would mean that they easily escaped. It wouldn't be the minimum speed to escape, right? The velocity has to just go to zero at this farthest reaches that the two particles can go away. They have to just have enough kinetic energy to take them out to the point where they have no potential energy left in the system and leave them at rest. Okay. And now once we have these before and after pictures, right, then the rest should be very straightforward. We just write down an energy conservation rule. The initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And I can see that written down. So now each particle initially is moving. So I have to make sure I account for the kinetic energy of both initial particles, and they're both moving with the VI. And then I write down, right, I use the potential energy term to express this thing, right? They each have a fundamental charge. One of them's positive and one of them's negative. So I end up with an expression that looks something like this for the initial energy expression. And I know that that has to be equal to zero, right? In the final state, we said they have no potential energy and no kinetic energy, so all those terms are zero in the final state. Okay, and that's basically it. Then we just plug in our known quantities and solve for VI, right? They gave us the initial separation. We know what those fundamental charges are and what K is, and we can look up the mass of an electron. Right? The only unknown here is that initial velocity, and we can just solve for that velocity. All right. I'm going to skip this for a second. There are several other examples in your book that you can work through, and I would urge you to look at them. So for example, 25.4 and also 25.5. We might have some extra time on Friday if people look at that and have questions about how those go through, but it's essentially the same process, right? You draw an initial state and a final state, find all the initial kinetic energy and potential energy in the system, and relate it to the final potential energy and kinetic energy, right? That's our problem-solving strategy for these potential energies. Okay, great. So now in the remaining time today, I want to move on to discussing electric potential. Okay. So what is the electric potential? Well, it has a really simple definition. This thing that we're going to call V, that's the electric potential, is equal to the potential energy, the electric potential energy, divided by the charge of some probe charge. Okay. So what are the units on electric potential? Well, it's like joules per coulomb. Okay. So an electric potential is not a potential energy. It tells me the potential energy that some particle would gain at a point in space that has that electric potential if I place charge a probe charge Q at that point in space. So what does that mean? It means if I knew that at this point in space that the electric potential was equal to, say, 20 joules per coulomb, okay? And then what I did is so the electric potential is a property of some space, right? Some region in space that I can place particles. And it comes from, right, it's generated by some source charges setting up an electric field, and we'll try to tie together that exact relationship in the next chapter. But just like the electric field was a property that gets established in the space around some source charges, electric potential is some property of the space that gets established around the source particles. And so now if I take and say I put in here some probe charge that has some, right, I could put in, say, a 3 nanocoulomb charged object at that point in space. Well, now I could calculate the potential energy that got added to this system, right? That guy is interacting in that place. The potential energy of the system is now 3 nanocoulombs times 20 joules per coulomb. Okay. And if I had doubled this charge, right, notice what happens is that the amount of potential energy in the system doubles. So it's just telling me, right, it's again, it's the amount of energy, potential energy that I'm going to gain if I drop a coulomb of charge at a specific point in space. That's what this electric potential is telling me. And right, this concept is important because it's nice to think about the space as having this constant property called the electric potential. Because we saw in, for instance, the form for the electric potential, right, for a point charge, or for the potential energy for a point charge, right? U for a point charge was this thing that was like K, Q1, Q2 over R. And the potential energy could be positive or negative depending on the sign of both charges, right? Now, what if we want to find the electric potential coming from a point charge? And let's imagine that it's sitting here in space. So there's some Q1 that's in space, and I want to know what the electric potential looks like around this thing. And I want to know what the electric potential is surrounding this thing. Well, I already know what the potential energy function looks like. If I put a probe particle here that's called Q2, let's say that's our probe particle. Well, I have that function there. So to get the potential energy, it's just going to be that point potential energy divided by the charge of my probe particle. It's just going to be K Q1 over R. Okay. So it's something that, right, it's a property. Again, this electric potential is a property that gets set up in space around a charge, and then another particle brought into the region of space around that source charge is experiencing that electric potential, and that alters or gives that system the potential energy that we can calculate just by multiplying the electric potential times the charge. Okay? So that's where this equation is coming from, right? For a point charge, I can calculate, I have a nice functional form for the electric potential around this various objects. What if I have lots of point charges, 1, 2, 3, right? Q1, Q2, Q3. And then I'm going to bring a probe particle somewhere nearby and want to know something about the potential energy here, right? I want to find the potential energy for this system by multiplying Q times V. Well, how would I do that? I would need the total electric potential at that point in space. And I could do that by calculating the electric potential coming from each individual object and adding it together. It just follows the superposition principle that we've seen so many times. Okay. And that means that we can do just like we did for the electric field. If I have continuous charge distributions and I want to calculate the electric potential at points in space around those continuous charge distributions, that I can just break them up into tiny pieces that are essentially point charges, and then use my superposition principle to sum up the contributions from all those little pieces and calculate the functional form for the electric potential around those objects. Okay. All right, I think we've talked about all that. All right, we'll come back to this. So let's try this problem here. I have 5 different configurations right, charge configurations, and we're thinking about what are the electric potentials that get established around these objects. And I have 3 different points drawn around each different charge distribution, and we want to rank in order the potentials, okay, the electric potential at the numbered points. Okay, we're going to rank them in order from highest to lowest. So let's set up a scale here. Let's see if it's 1, 2, 3, or if it's 3, then 2, then 1, or if it's 3, 1, 2, or if it's 1, 3, 2. Oh, I don't have enough spaces here, right? All right. Okay. Let's see if I don't know if this is going to work. I don't know if I have enough choices on our poll to do this here. So if it's F, right, this last one could be 2, 3, 1. If it's F, I guess just don't respond to the poll, and I'll know that means it's the one not on this thing. I should have extended the poll today. Apologize. So let's look at A here. I have a positive charge sitting here, and I'm looking at these 3 points here. How do we rank the electric potentials coming from these guys? Okay, let's go ahead and end the poll. So let's see. We know that that's a point charge, and we said that the potential around the point charge looks like K, Q over R. Okay. This is a positive, right? This is a positive charge, so these are all going to be positive values. As I get further away, what happens to the magnitude of this thing? It's going to decrease. So the smallest one is going to be 3. What about 1 and 2? How do they compare? Well, they're both the same distance away from this charge, so they're actually equivalent to one another. So you could have said 1, 2, 3, or you could have said 2, 1, 3 in this example, and you would be right. Maybe we'll just have you instead of the poll for this one, since I didn't give enough choices. Maybe we'll just have you write the order into the chat when I ask you to. Okay, so let's look at example B. Now I have a negative charge. Okay. Let's rank and order the potential at points 1, 2, and 3 for a negative charge, and I want you to tell me that their ordering, which is largest, which is smallest, which are equal. How does that go? Okay, good. I'm getting a lot of 3 is greater than 2 is equal to 1. Okay, good. So let's convince ourselves that that's right. Again, using that formula we have up in the top left, now we have a negative charge. So the closer I am to the object, the larger, right, the more negative my electric potential is. We see that the 1 and 2 again are the same distance away. So I know that 1 is equal to 2 in this example. But because 1 and 2 are closer to the object, so they should be more negative. So those guys are going to be smaller than 3. So 3 is largest, and 2 followed by 2 and 1, which are equal. Okay. Now what about C? So we have a doubly negative charge, right? So this has some value minus Q, or sorry, minus twice Q. This has value Q sitting on it, positive. How do we rank the potential energies around this guy? Why don't you put your thoughts into the chat? How do we rank those not potentials, energies. How do we rank the electric potential around those two? Okay, I'm getting a lot of 3 is largest, 2 is middle, 1 is least. Let's go ahead and write it down. So for 1, I've got a contribution for the electric potential coming from 2 sources now, this negative charge and this positive charge. And I can use my superposition principle to find the total electric potential at that point. Okay. Let me just say that the distance, right, we see that there's this kind of equal distance everywhere here. Let's just call that R. Okay. So point 1 is got a potential from that negative 2 that looks like, minus Q2 over R. And then plus from that positive guy, it's going to be like K Q over 1, 2, 3, right? This guy is 3R away from that guy. Okay. What about 2? It's equal distance away from each of them. So it's going to be like minus K twice Q over R plus K Q over R. And for 3, again, I use the superposition principle. Now this guy is closer to the positive charge, and he's 3R away from that negative charge. So it's going to be like minus K 2Q over 3R plus K Q over R. Okay. And now I just need to, right, I can basically just ignore all the constants here and just focus on, right, the numbers, right? So this is like minus 2 plus a third. This one is going to be like minus 2 plus 1. And this one is going to be like minus 2/3 plus 1. Okay. I just factored out the constants, right? These are the scale factors that would sit in front of my common collection of constants in these things. Okay, and so now I can compare these things, guys, right? This thing is going to be, what is this going to be? 6/3 minus 5/3. This guy is going to be -1, and this guy is going to be 1/3. Okay, something like that. And now I can easily compare which one has the largest potential. Right, 3 is largest, 2 is second, and 1 is smallest. Okay, what about D? Now I have a parallel plate. Okay, positive charge on the left, negative charge on the right. I can flip back, and your book goes through and does a calculation. We can solve for what the potential energy or the change in the potential energy looks like between a parallel plate capacitor. And it has this functional form, right? The potential energy is essentially equal to ES, where S is measured from the negative plate, right? That's the distance from the negative plate. And we know that the value for an electric field between these two plates, right? We saw that before, is like the charge density built up on these plates, okay, divided by epsilon naught stuff, right? It's got a uniform electric field between them. And if I put more charge on it, I get a stronger electric field, or if I change the surface area that charge is spread out on. Okay. So V equals ES. Okay. Again, this is measured from the negative plate, right? The electric potential is increasing as I move towards that positive plate. Okay. So what's happening in this example? Well, now I need a coordinate system. I see my negative plate is on the right-hand side. So my electric potential is growing like ES, that distance that I am away from the negative charge. And so my electric potential has to be growing as I go towards the positive plate. The electric potential is going up as I move towards that positive plate. And so what does that tell me about the rank between these different particles? Well, look, the only thing that matters in determining the electric potential between these two plates is how far you are away from that negatively charged plate. I can see 3 and 4 are the same distance away from the negative plate, and that 1 and 2 are the same distance away from the negative plate as well. So 3 and 4 are equal in this example, and 1 and 2 are equal. Okay. Which one is larger here? Well, the plates 1 and 2 are further from that negative plate, so those guys are larger than 3 and 4. Okay, something like this. What about E here? This is the last one we'll look at for today. I've got 3 points, 1, 2, and 3 sitting there. And all we're seeing now is the electric field. All we're seeing now is the electric field. And we want to rank the electric potentials. So we're going to go into this in more detail in the next chapter. But the important thing to notice is that the electric field tells me about how the electric potential is changing in space. Okay. So you can see this expression from what we have written down for this capacitive plates. There's a relationship between the electric field and the electric potential. And it tells me that if I move some distance through a fixed electric field, that my electric potential is going to be increasing. What direction does the electric field point in this case. Remember it moved, oops, sorry, wrong. The electric field points from the positive to the negative plate. So if I'm moving, right, what we can see here is if I'm moving against the direction of the electric field, my potential energy should be increasing, right? Just like we would expect from the energies. So how is this, how would we rank 1, 2, and 3 in problem E? What do we think? Okay. So the answer here, right, is if I move this way, right, you can see if I move from 1 to 2, I'm moving upstream against the electric field. And so that means that my electric potential has got to be increasing, right? That's what we see all. So like for the point charge, we see the same thing, right? The electric field points away. The electric potential is equal to KQ over R, right? And so as I move against the electric field, my electric potential is increasing. So this is the general relationship. We're going to be more exact about this. As I move against, if I move against the electric field, my electric potential increases. And so here you can see as I move from 3 to 2 to 1, I'm sort of swimming upstream against the electric field. And so the electric potential for 3 should be smaller than the electric potential for 2, and then finally 1. 1 has the larger electric potential. Okay, good. We're going to keep going with this and wrap up this chapter tomorrow. So please bring your final questions. If you have anything that's not clear, ask that tomorrow, because that will be your last chance, at least in class, to ask before homework is due. Just to remind you guys, if you want to set up times, office hours with me, please just contact me, and I will arrange a time to meet with you. That's another reason why we're not having live lectures on Monday, is so that I can have plenty of time in my schedule to make sure I can meet one-on-one with you if you need to. So don't hesitate to reach out. Okay, guys, that's it for today. Thank you so much. I'll hang around for a couple more minutes if you have any final questions, but the rest of you are free to take off. Thanks so much. Have a good day. Bye, everyone. Jacob, is it like a specific homework question or like a general concept thing? Okay,
Hi, can you hear me?
I can hear you, Jacob. Hi.
Hi. It was just one of the homework problems. It felt like there was a typo because it basically was you had like a rectangular surface that had um it was like vectors I and j, and it wanted you to find the flux if you had a certain um electric field vector. And so it gave me you had two different ones to solve. You had one vector that was I and k, it had the unit vectors I and k, and then another one had unit vectors I and j.
Okay. You were wondering if that was
And
a mistake. Yeah.
I was wondering because like the one that was going through the surface, it said it was 0, and then the one that was parallel to the surface, it had a flux. I thought that was I thought
Okay.
had to be perpendicular for a flux to
Okay.
be possible.
Yeah, can you send me the problem number in Slack or an email, and I'll take a look and get back to you. I don't know the details that well off the top of my head, but I'll
Alrighty.
definitely go take a look at it.
Awesome. Thank you. I'll send it
Yeah,
to you.
yeah, please do. Thank you so much.